And since I have not gone through and graded quizzes at this point, I'll open it up briefly to any, if you have any questions you want to ask me about the quiz. In person, can go through any of those. Otherwise, I will show you this while you're thinking about that. I'll show you this again. I can't keep all my stuff straight while I'm trying to talk and log in at the same time. This is a really cool website called Frontiers In. And it's basically, it's really interesting for those of you who think you might want to get into research in the future. Because there's a whole section where basically it basically keeps a list of, and this is not the one that I was remembering. Basically, it has a list of like what are the common research areas right now, and it does look like they've changed their structure a little bit. Now it looks like they're predominantly in open access articles, which is still pretty cool. It's just not what I thought it was anymore. There's some interesting stuff. Yes. Okay. So Frontiers In, and then you pick a topic or a journal, and it's got all sorts of interesting things. Frontiers in Behavioral Neuroscience, for instance, and it'll give you a bunch of articles. What's common research going on in here. And the cool thing is that when you find something here, it's going to be an open source article, so you won't hit a paywall in theory. Emergence of substituted phenethylamines, dependence, abuse, and toxicity. It's about time we had some research in that area, considering those are most of what are considered, the designer drugs or research chemicals that were really popular in the late 90s until, well, like the mid 2010s.
What it looks like.
Yeah, you've got cathinones, you've got, yeah. Everything from MDMA to the 2C compounds to substituted cathinones like bath salts. There's a lot of chemicals that have a lot of potential for abuse, but very little is known about them. Even all the way down to it's, in a lot of times they don't even know how to test for some of these compounds because there's so little research done, but they're still being sold as drugs and people are taking them. So interesting field. And maybe there's another, I'll have to look around and see what the other, I had another thing in particular that allowed you to click around to, it was like more of a web structure, would allow you to click around to different research areas. And it was focused more on physics, and it was more outreach oriented. That one, it just gives you a list of things that are in this area. But it is, at the very least, it's got a cool, interesting way to scroll through and find what's going on in different areas, what are hot areas, without hitting any paywalls. You can read abstracts to your heart's content. Yeah. Might be fun. Make sure I did hit record. And looks like audio is working today. So, all right. So did anybody have anything about the quiz specifically that you wanted to ask about? I'll throw it up real quick. That was this one, right? It was one that, like I said, so the material wasn't that hard from the last two chapters, right? There was just a lot of it when it comes to mechanisms, right? So, okay.
When you are looking at this,
Yeah, this one.
You're rotating the ball. What is the goal of that rotation? How do you know what you
You can rotate it any way you want. The goal is to make sure that you take this planar molecule and you want to put the OH, the carbon, the allylic carbon with the OH away from you and to the right. Or if you're going to picture it being flat, you want it up and to the right. Just because that allows us to keep track of pluses up and minuses down. If you don't put the OH either into the board into the right or up into the right, then you can't use that plus means you put the epoxide up rule. Right, so it's a very straightforward rotation. It's not nearly as complicated to do these rotations as it is when it's a tetrahedral carbon. It just allows you to keep track of that, of which specific isomer we're going to wind up making. Right, so for this one, we would want to flip it. If we flip it like a pancake, so if I'm drawing, where's the red? The way that I would visualize this is think about that as being an axis of rotation. We're going to flip it. That's supposed to be an arrow. Like that. So we're going to take it and rotate it. So it's still flat. So flip it like a pancake. And that just puts it so that it really looks almost the same. Like that. And now we can say, okay, because it's a plus DET, that means the epoxide is going to form upward. If you didn't flip it to put the OH up and to the right, then it gets a lot trickier to figure out, to visualize. So it's just a easy way. And it shouldn't feel that tricky. It should feel almost too easy because it is. It just is almost like a bookkeeping thing, like crossing your T's and dotting your I's.
Yeah. So I was looking at practice that
Mm-hmm.
class. It was draw the same way as
Mm-hmm.
on the with as it's drawn in the place with the carbon.
So with the carbon oxygen to the down and to the right. So we didn't flip it, which means, so if we flipped it and if it was minus, so if we take this one that we just made and we flip it back the same way so that that carbon with the OH on it is down and to the right again, now we wind up with that compound, right? So if it was minus DET and we didn't draw it flipped up and to the right, or if we did and then flipped it back, then it would give us the opposite of this compound, and it would, which would be out towards us. Right? So it doesn't, I don't think what you have written is wrong. I think maybe you didn't, either we didn't show the work, all of the structures, the flipping it the other way, or maybe you did it mentally and didn't draw in the flipped state. You said, oh, I would just flip it like that so I can just draw it minus means up instead.
Yeah. Well, basically either one
Let me see your notes. Let's take a look. I don't want to say that your notes are wrong. This should be right.
I'm not sure if maybe I just wrote that.
I think that you did show it flipped, and then you use the minus instead. This is wrong. And you're absolutely right to pay attention. The whole point of doing the flip is that we don't mix it up. Always do the flip. Because then you can use pluses up, minuses down. All right, so for question 2, just a quick recap. What stereoisomer do we get? We know we're going to add, the bromide is going to attack. It's under acidic conditions, which means the first step is protonating the OH, or the oxygen, and when you do that, that weakens the bond to the more substituted carbon. So basic conditions, you go with your gut with sterics, and your nucleophile attacks the less substituted carbon. If it's acidic conditions, you weaken the more substituted bond, the bond between the oxygen and the more substituted carbon. So once it's protonated, this bond gets weakened. And this, between the strain of the geometry and weakening that bond, that means that we can do an SN2 attack on a tertiary carbon. So because it's acidic, and the first step is protonating that oxygen, we're going to put the bromine on the more substituted carbon, and we have to do the umbrella flip to do it. So our final product here is going to look like carbon that's on the right with an OH up and in the plane, and a methyl coming out towards us. On the other side, we still have the ethyl so C2H5 is the other way, the condensed structure for writing ethyl, just to make sure we're thinking about that. And we have the up and into the board, we have the phenyl group. C6H5 is a common way of abbreviating that, as, or we could write pH if we wanted to. And down and in the plane is our bromine. So with stereochemistry, with epoxides, it's a little tricky in that acidic versus basic conditions changes where you attach your nucleophile. But you have to start with enough information about the stereochemistry that it's not that hard once you remember it's just an SN2 attack. Everything already has to be drawn more or less in the right spot. You're going to do one little umbrella flip and remember which bond gets broken. And that's all there is to it. Right? So the trick is just in remembering acidic versus basic conditions is the trickiest part, really.
So like all of it.
So you invert the one that the bromide attaches, but when I say everything stays where it is, I mean that not that it stays R versus S, Just that if it's out towards the board, it's still out towards you, or if it's into the board, it's still into the board. It just flips from being down to up, which typically has the result of that means it'll go from R to S, but priority means that we can't generalize with that, right? Because depending on how the priority changes, we could conceivably have it still be S, but have been inverted. All right, anything else for right now? And like I said, I'll grade the rest of these and give a little bit of feedback later. For the most part, if you've got your reaction summary in front of you, the trickiest thing is an enantioselective and acidic, and remembering acidic versus basic. All right, we're entering the last chapter for this quarter, which seems a little early for that, but it is week 10. And this is a tricky topic. We're going to come back to kinetic versus thermodynamic control a little bit. And we're also going to talk about orbitals again, because this class of reactions that we're going to talk about with conjugated dienes, it turns out we have to know what the orbitals look like to know which product we make. If we don't know what the orbitals look like, then we're going to draw the wrong product, at the very least the wrong stereoisomer, but sometimes the full-on wrong product entirely. So we're going to take our time with it because it's got some tricky concepts. We're going to talk about research that won not one, not two, but 3 Nobel Prizes in the last 50 years. One of them should have been earlier, but he was Japanese, and Japanese chemists and scientists didn't really get the respect that they probably deserved, not probably, that they deserved, mostly as a result of being on the losing side of World War II and being from Asia. So research that won Nobel Prizes much earlier, would have won Nobel Prize much earlier had he not been Japanese, which is sad, but at least he won a Nobel Prize. It's not quite like a Rosalind Franklin situation. It's just close. All right, so dienes are really not a new functional group. A diene, a diol was 2 alcohols, right? So a diene means you have 2 alkenes in the same molecule. And there's 3 types of dienes, and some of them are really no different than alkenes. So, oops. The simplest form of dienes are what are called isolated dienes. And isolated dienes are really straightforward because there's no resonance. Because you've got an sp3, at least one sp3 carbon in between, you basically have a barrier to resonance. It means that you really don't have a diene, you have 2 alkenes. And it really just behaves as though you had, you could treat each of them as just being its own functional group. There's no interaction between them whatsoever. The least common, but also relatively simple as far as how they react, is called cumulated dienes, or also called allenes. Cumulated dienes, when you have 2 alkenes attached to the same carbon, still can't have resonance, right? Because these orbitals are perpendicular to each other. The 2 p orbitals, the 2 pi bonds, have to be perpendicular to each other, just like we see with CO2 or with cyanide for that matter. Because they're perpendicular to each other, there's 0 orbital overlap. And again, going back to linear algebra terms, they have to be orthogonal to each other to be a part of the same, to be attached to the same atom. So in order to have them be orthogonal to each other, that means by definition, they can't overlap. So even though it seems like maybe there's a little bit of spatial area where they could overlap, the fact that they're attached to the same carbon means by definition, they can't resonate. They can't have any overlap, which means once again, they're going to react like they're independent alkene groups. And they're going to react the same way that any alkene would from back from, was it chapter 8, maybe when we first did alkenes in addition reactions? 8 or 9. I think 8 was alkenes and 9 was alkynes. Which leaves this middle class. This middle type of diene is the kind that we're going to spend the most time on because they're the most interesting and because all of a sudden the fact that it's a diene changes how it reacts. The fact that they're conjugated, meaning that they can have resonance, means that you don't get the same products as though there was just one of them. Right? For the ones that I circled in red, just ignore the fact that there's 2 alkenes other than for stoichiometry. If they're conjugated, we've got resonance, and that's going to change how things work. And like I said, for the most part, we only care about dienes as being a separate functional group. Isolated dienes show up, but there's no point studying them separately. We already had a whole chapter on alkenes. Accumulated dienes are so uncommon that we don't really study them specifically, and they do react really similarly to isolated dienes. So, and the reason that we have these orbitals here is to really illustrate how that resonance happens. Because you don't have an sp3 carbon in the way, and they're not attached to the same carbon, they're attached allylic relative to each other, we can have those pi bonds oriented in the same direction, which means that we don't really have 2 separate pi bonds. We don't have a pi bond here and a pi bond here. It starts looking more like a benzene ring, where that resonance allows one massive bond as instead of isolated separate pi bonds, which all of a sudden makes them more stable too. All right, so just quick practice. Really want this to go on the side, but let's identify whether each carbon-carbon pi system, so we're talking about the entire group now, not just one pi bond, is it cumulated, conjugated, or isolated? So for cis, aconitase is the enzyme that does this, but I can't pronounce aconitic acid. Aconitic acid. We'll go with that. Is the carbon-carbon pi bond conjugated, cumulated, or isolated? Or both, or all 3? Right, there is no other carbon-carbon pi bonds. So the carbon-carbon pi bond that we have right here, it's conjugated with these acid groups. It's isolated from that acid group. But we don't really have another, it's not a diene though, right? So I started with a bit of a trick question. But it's still worth it. Saying, okay, the ones that are in red are conjugated with each other. And the one that's circled in blue is isolated from the ones in red. Yes. We don't get the same class of reactions happening, but we do get similar overlap. This whole thing, so in theory, all the ones circled in red the single bonds in between the different functional groups should be free to rotate, right? Because it's just a sigma bond, right? So we should have free rotation happening there. But what we actually see is this whole section where it's all conjugated will actually stay planar relative to each other in order to maximize that pi bond overlap. And there's actually a transition state for just for doing a rotation around a sigma bond. You have to break that extra resonance in order to rotate around that bond. If we wanted to flip that oxygen so it was facing the other way, there's actually a transition state, and then it reforms another pi bond once it gets to the other side of that rotation. How about oxamine, or probably osamine, since there's only one C? Isolated and conjugated. Which part's conjugated? So conjugated, isolated. Good. How about jasmine? As you might guess, it's found in jasmine flowers, but it's a ketone, so it's jasmone. Those chemists, so clever. The carbon, the alkenes are isolated from each other. The group on the left, those are conjugated, but they're isolated from that group. And the one circled in red is isolated from everything, has no resonance. And on the right-hand side, or sorry, the right-hand molecule, carbone. Conjugated. Isolated. All right, so really we're just looking for those alternate pi bonds to make it considered conjugated. All right, so if we want to make a conjugated diene, it's actually really easy to make a conjugated diene because it's more stable when you have that extra resonance, right? So it's similar to how we would make an alkyne. We do a double elimination, except we don't use a base that's as strong. If we use a strong base, but that's not as strong as amide, especially if it's sterically hindered, that allows us to make this conjugated diene really easily. We just need, basically you need two good leaving groups within about 4 carbons of each other, right? The two leaving groups could be anywhere on this molecule, other than you can't have them on the same. Okay, so you need them separated at least a little bit. Spatially, they can't be on the same carbon because then you might wind up making more alkyne than conjugated diene. But the conjugated diene is more stable than the alkene, or sorry, than the alkyne because of that resonance. So we can either, if we have a dihalide, we can do a double elimination, or if we have a alkyl halide that is either allylic, or even if it was attached here, in either of those two positions, on the alpha carbon relative to the alkene or on the beta carbon relative to the alkene, either way, when you do an elimination reaction, you're going to make the conjugated diene. Right, so we have the benefit of that extra resonance makes it so much more stable that we can just rely on the fact that rely on thermodynamic driving force, basically, to make the product we want. It's a lot harder to make accumulated diene because you are usually competing with making a conjugated diene, which is more stable. And here's some energetic proof of that. So if we look at the energy that's released when if we hydrogenate butene twice, we're downhill in energy 254 kilojoules. But if we hydrogenate 1,3-butadiene twice, it's only downhill in energy 239 kilojoules. So it's less downhill in energy to hydrogenate a conjugated diene than an isolated diene. So this is sort of this is basically going back and using Hess's law, which was that was the rule that said that we can add up chemical reactions and cancel out things that are both a product and a reactant, and then we can add up their energies at the same time. And so this is not taking into account entropy. This is just looking at bond energy, just enthalpy. And when you do that, normalize it and make sure everything's balanced, we get this difference of 15 kilojoules. It's 15 kilojoules per mole more stable to have them conjugated rather than isolated. And the slide says, why might that be? But I've already said the word plenty of times today, right? The R word, yeah. Resonance, because we get resonance. And remember Ron, Harry, and Hermione. It's always resonance, sterics, and electronegativity. One of those three guaranteed in this class when I ask a why question. And we actually get two distinct conformers, a little bit like what I was talking about earlier when we were talking about conjugated with the carbon-oxygen pi bonds. If we were just looking at sterics, and we were going to look at 1,3-butadiene, so we didn't specifically go over the nomenclature. But I think you can probably see how it works, right? Buta means it's 4 carbons. Diene means that there's 2 alkenes, and we just specify where each of the alkenes are. So 1,3-butadiene, there's carbon 1, there's carbon 3. So 1,3-butadiene, we might, if we just looked at sterics, we would expect that these things that everything should try and stay out of everything else's way, right? Because if we, let's see, if we have how can I show this easily? And we'll look at it in Moldia. So if we were just looking at sterics, we might expect that this is not necessarily the most stable form, right? Because we kind of have this hydrogen here is kind of going to be pointed in the same direction as this hydrogen here. We would expect them to be not quite planar because they're going to sterically interfere with each other. But when we actually look at this and optimize the structure, and actually there's some built-in ability for it to do some, let's see if this do it properly. So it's thinking, calculating. Basically, when it calculates that, it's going to move everything around, all the different atoms around, to see if there's a lower energy state, to give it a better geometry, a more stable geometry. We wind up, when we do that, it stays linear or planar, right? Because that's how it does have some steric interference when we do that. But on the other hand, it allows us to maximize resonance, maximize orbital overlap when these things are totally planar. Right, so that means that there's really two forms it can be in then. It can be in the what's called the S-cis. S stands for the sigma bond. The sigma bond can be cis, or the sigma bond can be trans. Right, and so normally we don't think of sigma bonds as being cis and trans because they can freely rotate, but not when there's resonance. So if we have it in the S-cis position, that means it's totally planar, but both of the pieces are pointing the same direction. Basically, we just treat the sigma bond like it's an alkene and say cis versus trans. Right, and so the S-trans is still planar, but you've got your two alkenes facing in opposite directions from each other. Which of those would we expect to be more stable? And why? Yeah, sterically, they're able to stay out of each other's way when it's in the S-trans. So just like when we were doing alkenes, we would say things like, okay, if we have a methyl here and a methyl here, we would expect the trans to be more stable slightly than the cis in this configuration, because the two methyls would bump into each other if it was cis, right? So exact same logic. We just have the resonance that means that it's going to behave almost like it's an extra pi bond in between these two. So which is why we have S-cis and S-trans. And this is really interesting for a couple reasons. So if we want to go from the S-cis to the S-trans, it's downhill in energy 12 kilojoules per mole, which is convenient, or I guess not convenient, makes sense, logical, minimizing sterics. The activation energy, though, is 15 kilojoules per mole. Why does that number sound familiar? Because we just used that, right? We just said that we get 15 kilojoules per mole extra stability when we have these things conjugated, right? Back from this chart. So essentially, to get it to rotate between S-cis and S-trans, we have to break that conjugation, which makes it energetically look the same as though it was isolated diene. We basically remove all the beneficial resonance in order to get it between these two states. And then we reform all that beneficial resonance, or favorable resonance, I should say, once we get it planar again. Right. Exactly. It's where was the one I was looking for? That one. It is this one. Yeah, this section right here, where you have that orbital overlap when they're conjugated, that's what you have to break in order to get it to go from S-cis to S-trans. And that's why it has that same energy amount, 15 kilojoules per mole, because we're breaking all that favorable resonance. And it turns out to not be at, the transition state is not at exactly 90 degrees. we would expect it to be at exactly 90 degrees. But due to this extra little bit of sterics, the 12 kilojoules per mole of sterics interactions we get, it's more like it's 110 maybe 120 degrees rather than 90 degrees. Let's rotational transitions. You will actually make this graph next quarter in lab. We'll actually calculate these energies using similar methods to what I just showed you on MolView, where it kind of tweaks all the geometries to find lowest energy. And it winds up being more like 105 degrees, 100.4 degrees. That's using BLIP, which is not great computational method, but it does okay in this case. So it's not quite at 90 degrees because of that extra interaction. So it's a little bit closer. The transition state is a little bit closer to the S-cis conformer because that's higher energy, forcing those two carbons to get close to each other. And this was just showing that if it's just an isolated alkene, that same bond right here, if we rotate around that same bond the same way, we get very little difference in the energy. It's only takes 5 kilojoules per mole to rotate, and we only get additional benefit when we get into a favorable conformer of about 3 kilojoules per mole, 2 kilojoules per mole. And so this is just illustrating, this is with no resonance, no conjugation. Rotationally, we're talking 5 kilojoules per mole. As soon as we introduce resonance, we're in a much larger ballpark. We're talking about much larger energies. All right, and it is to go back to the language we used back in first quarter. It's the most stable conformers for 1,3-butadiene are in an eclipsed state because that allows us to have that resonance. Right, so cool. That's interesting, I guess. Why does it matter? Well, we're gonna go back and I think this is in the wrong order a little bit. So let's talk about how this shows up in thermodynamic versus kinetic control for a reaction that we are well acquainted with. If we just have the addition of hydrobromic acid to an alkene, it's Markovnikov addition, right? We start by protonating, breaking a pi bond, and then that makes a carbocation that's a target for the bromide, right? If we do this with a conjugated diene, we wind up with a mixture of products. We get some of the 1,2, what's called the 1,2 adduct, where we added a hydrogen here and then on carbon 1, and then we added the bromine on carbon 2. But we also get some of what's called the 1,4 adduct, which, again, when I show you this, that kind of makes sense to some extent, right? Because the intermediate, actually, brought in black. Our intermediate is going to look like this, right? We start by adding a carbon hydrogen bond, makes the carbocation, breaks one of the pi bonds, but now we've got a carbon, a carbocation in a neallylic position to the remaining alkene, right? Which means we can have resonance. And the other resonance structure here then is going to look like this. So makes sense we would have two different products because we have two different resonance structures that have a positive charge for the bromide to attach to, right? Where it gets a little bit interesting and where we did not talk about this back when we first introduced this reaction, we hadn't talked about kinetically favored versus thermodynamically favored yet. If we do this reaction in an ice bath, we favor the 1,2 adduct. Meaning we favor the product where that looks like this. If we do it at 40 Celsius, we favor the 1,4 adduct. So the fact that changing the temperature changes which product we're making tells us we've got one of those crossovers between kinetic and thermodynamic control. So which one is kinetically favored and which one's thermodynamically favored? Who remembers how we could determine that? 1,2 is kinetic, because remember at lower temperatures, things don't have as much energy to get over that barrier, right? So you can only make the product that is easier to get over the barrier. At high enough temperatures where you have enough energy for everything to go back and forth as many times as it wants, you're going to wind up making the product that is favored at equilibrium. And that's the thermodynamic product, is the one that's got the most stability overall, the one that's most downhill in energy. So we'd say that's the kinetic product. That's the thermodynamic. Right, and that's what we see. We can actually calculate these energies too. We find the energy of the reactants, and we can find the energy of the first transition state, which is the protonation. And that's the same regardless, right? Because it's the same exact reaction up to that point. It only changes once we get to this intermediate where we have resonance happening. And now there are two choices. Your nucleophilic attack could happen on carbon-4 to give the thermodynamic product, or a nucleophilic attack can happen on carbon-2 to give the kinetic product. So what is it about the 1,4 adduct that makes it more stable than the 1,2 adduct? Why is there a difference in these two energies? Sterics? More substituted alkene. So that was before we talked, Markov-Makov was addition reactions, right? So what was the related but opposite rule for elimination reactions? Anyone remember Markov-Makov's classmate? Zaitsev. Zaitsev's rule is you make the most substituted alkene, right? Because more substituted alkenes are more stable. So the difference is partly sterics, because we've got this big bromine in the middle as a which is going to be bumping into this other group as well. versus having the bromine on a primary carbon, where it can be out by itself, and making the more substituted alkene, an alkene with two substitutions instead of just one substitution, is more stable. So those are the two factors that affect why the 1,4 is more stable thermodynamically. What is it about the 1,2 adduct that makes it the kinetically favored? Carbocation stability, right? Our two choices for our resonance structure look like this versus this, right? They're both stable resonance structures, but the one that puts the carbocation on a secondary carbocation is more stable than a primary, right? So in other words, again, really these resonance structures are both happening simultaneously, but in terms of statistics and probabilities, we can think of them as though there's a certain percentage of the molecules are in each of these states. So it's a little less representative of reality, but it makes sense in terms of predicting this. There's a higher probability that a bromide runs into this resonance structure because that's the more stable of the two. There's still a finite probability it runs into this structure, but that's less likely. I guess probably the best way to phrase it that is both accurate and shows what's going on here is that there's not a whole positive charge in either of these resonance structures because it's really adding both of the resonance structures together at the same time. It's quantum, right? So it's alive and dead in Schrodinger's cat world. You can think of it like there's 0.6 of a positive charge here and 0.4 of a positive charge on this one. They're weighted like it's a weighted average. So the fact that the one with the positive charge on the secondary carbon is more stable means it's going to have a higher weight, which translates to a higher effective positive charge or being more attractive to a bromide, to a nucleophile. Right, so kinetically, we favor the 1,2 based on carbocation stability. Thermodynamically, we favor the 1,4, well, and more generally, we favor the more substituted alkene based on Zaitsev's rule. More substituted alkene is more stable. All right, that's we'll come back and do a practice mechanism here, show the two possible products and say which one's favored. And then we'll talk about frontier orbitals. It just reminds me of that. So anybody ever get that song Frontier Psychiatry stuck in your head? 90s, like early glitch pop, plunder phonics. That was the style of where make whole songs just out of samples from other songs. Frontier Psychiatry. I think it was by a group called the Avalanches, if I'm remembering correctly. Frontier Psychiatry. That boy needs therapy. Frontier Psychiatry. Anyway, all right, come back 5 after and we'll talk about orbitals. So
You just read that song.
I did. So when I upload it to YouTube, YouTube's they edit it out because it's either that or if they keep it in there. There's basically they have algorithms that go through and will catch any copyrighted material and either force me to pay money to that group, or it just cuts it out of our recording. So this is talking about lithium ion batteries. This is a chart that looks at this is backwards. That's not the one I wanted. If you look at the green line here, it's what happens. Lithium cobalt oxide is the cathode in a lithium ion battery. And as you go through charge discharge cycles, the capacity, the amount of energy it can hold drops, basically because you wind up making products as side products for these that wind up breaking down the cathode material. And so over time, it stops retaining charge. And you can see that, after 120 cycles, you're down close to 50%. And it'll keep going eventually if you kept this chart going. One of the things that's really interesting about battery research right now is research that's going on in cathode and anode materials trying to prevent this. And so if you take lithium cobalt oxide and you deposit using this process called atomic layer deposition, where basically you do this gas phase on a surface where you deposit a single layer of aluminum atoms on top of the cathode, and then you evacuate all the gaseous product that's left, and then you deposit a single layer of oxygen on top of that, and then you can basically alternate what gaseous reactants you're using to deposit one layer at a time of aluminum oxide on the surface. And what they found, the reason I know about this is because the guy who discovered this is from University of Colorado. And so my best friend in grad school did the computational side of his papers, trying to model the surfaces and what happens. If you do 2 cycles of atomic layer deposition, you wind up dropping your initial specific discharge a little bit, but then basically it protects the cathode and you don't wind up with the battery degrading as fast. You wind up after the same 120 cycles, you're still up at, I guess you were not in percentage here, where you still are close to 100% though. You're still 90% of the capacity compared to going from 175 down to 75, losing more than half of it if it's uncoated. And then so this is a paper that a figure that they used all the time in all of their group talks, anytime somebody had to defend their dissertation or present research. And from the George group, they always use that exact figure because it very clearly lays out what's happening. And it's pretty easy to understand. But I don't think that this has entered production yet, because I believe that the atomic layer deposition process is actually patented by Steve George. At least maybe it's a type of patent where an application patent where he couldn't patent the process, but he can patent using the process on cathodes specifically. So I don't think that it's entered much widespread use yet, or Steve George would be a billionaire. And maybe he is. He's an interesting guy. But anyway, cathode materials, really interesting research happening right now. The big chunk of what Elon Musk is doing with Tesla, it's not actually about the electric cars, it's about the batteries.
I actually, in previous chemistry classes, chose how to make a better battery and that topic. And because everything was patented, it was so hard to find information.
Yeah, they have to make the information public to the patent office, but I think that they can make the case that if it's too easy to reverse engineer from the patent application, that the patent office can redact a lot of the details. They have to tell the patent office enough that the patent office says, okay, yeah, that's worthy of being a patent, but the patent office doesn't have to release everything. And there are some institutions like 3M and Dow, I think, do use a process where they don't patent things. Because rather than do that, they just rely on operational security and word not getting out basically about some of their secrets. So basically, like it's like the secret formula for Coca-Cola really is a secret. They don't patent it because then they would have to disclose it to the patent office. And after a certain number of years, the patent office makes it public and anybody could use it and you could have generic Coca-Cola.
I think what those guys is they would say, we really allow the import of the in the United States.
They're not the only one. I think Hanson's sodas for a while were making, it's, oh, coca leaves is what you said. Cola nut, is the other part of Coca-Cola. Cola nut is actually where the caffeine comes from in most colas. And there are a couple brands that still use cola nuts for some of their flavoring in colas. I think Hanson's was one of them. And I think there's some other like natural soda products these days that have cola nuts. But you might be, I think they still might use some, they extract some of the flavor and then remove the cocaine from it. Right, they can't do anything with the cocaine. Yeah, no, it's a thing. Explains a lot about the South, doesn't it? All right, so what are our two possible products for the hydrobromination of this diene here? Actually, there's more than two. So we could make, if we're drawing, I'm gonna draw all of them first, and then we'll pick the most favorable. No. So you could get the 1,2 adduct that puts the bromine at the bottom. You could get the 1,2 adduct that puts the bromine at the top, which was going to have an R plus an S. Or you can get the 1,4 adduct that puts the bromine, nope, sorry. That puts the bromine at the top. And again, R plus S. And you could get the 1,4 adduct. Puts the bromine at the bottom. And again, R plus S. And I suppose this one's also R plus S. They're all going to be R plus S, right? Because they're all going through a planar intermediate, carbocation intermediate. The ones in blue are the 1,4 adduct. The ones in red are the 1,2 adducts. And at 0 Celsius, we favor the kinetic product, right? And the kinetic product is the 1,2 adduct. And actually, specifically, we actually can't even make that generalization here, right? Because we have to look at what the intermediate looks like in both cases in order to say what the kinetic product is. Because we'll use pink. The 1,2 adduct, the intermediate for these two, let's see, for this one, the intermediate for that one puts a positive charge on a tertiary carbon versus a secondary carbon, right? So these two are getting compared to each other. The 1,2 versus the 1,4. And that's our kinetic product because the intermediate has a, the intermediate resonance structure can put a positive charge on a tertiary carbon for this product. And the one below it is the intermediate has a positive charge on a secondary carbocation or secondary carbon, right? So the one that's circled in pink is the kinetic product out of those two. The other ones, both of the resonance structures for the intermediate are secondary carbocations, right? Which means there is no real difference in kinetics between these two. So the rate constant is going to be relatively the same because their activation energy is going to be relatively the same. And they both have the same substitution, right? So there's not a thermodynamic product favored out of those two either, right? So at 0 Celsius, the product that is going to be most favored is going to be the top right option. Right? Because all of the others go through a resonance structure that puts a positive charge on a secondary carbon. The one that's in the top right is the only one that goes through a resonance structure with a positive charge on a tertiary carbon. And there's not any of them that are, all three of the others are going to be relatively equal in terms of thermodynamics though, right? Because they all go through a secondary carbocation resonance structure. They're also all making a tertiary or an alkene that has 3 substitutions, right? So all 3 of these are all roughly the same in terms of thermodynamic stability at the end. So if we said at high temperatures, we're going to expect relatively equal amounts of all the ones that are circled in green. I mean, maybe measurable differences, but in terms of their energies are all pretty close together. So little things like sterics can wind up making a difference of 2 or 3 kilojoules per mole, which could wind up being a 10% difference in yield pretty easily. But they're all going to be measurable amounts if we're under thermodynamic conditions. But if we're under kinetic conditions, we're going to favor the one that's circled in pink pretty heavily. So this is a particularly complicated one because we have 2 different carbons that we can protonate to start this whole process. If it was a more symmetrical molecule, it'd be a little bit easier to see, or you would get more definitive, you have fewer products and more definite answers between them. All right, so let's talk about orbitals a little bit more detail. Anytime we make bonding orbitals, which happens anytime we have atomic orbitals overlapping, Nice. So you can have atomic orbitals can overlap to make molecular orbitals, and those molecular orbitals, the sp3 orbitals, can overlap to make bonding orbitals. Right. So in terms of the way this works is atomic orbitals, S, P, D. We know what the shapes look like. We can follow along electron configurations on the periodic table. Those hybridize to give us molecular orbitals and geometries like sp2, sp3, sp. Those are the hybridized molecular orbitals. And then those hybridized molecular orbitals, when they overlap with the molecular orbitals from other atoms, can wind up making bonding orbitals. And the mathematics behind it is just a linear combinations of these functions, right? We had specific functions, 3D functions in polar coordinates for s orbitals, p orbitals, d orbitals. When you add those together, you say, okay, I'm going to take 33% of an s orbital, and I'm going to take 70% of a p orbital. Then you get the molecular orbitals, and it just looks like you took these two functions and added them together. So if we said an S was just, so let's say an S orbital is f of x equals x. And we could say a Y is g of x. We say it's x squared. It's not what the functions actually look like, but just for the sake of showing how linear combinations work. If we have an sp orbital, it would be f times a g. So x times x squared. And all of a sudden we have a new function that's a combination of the functions before it. Really, it would be a plus, not times. We represent them as sp pushed together. It would be, but you know, an SP would be f plus g. So x squared plus x. And all of a sudden we have a new function that's a combination of the two other functions. So we basically just have these layers of starting from basic atomic orbitals. We can make things more and more complex by just gradually mixing them together more and more times. And then you take the results and mix them together, and you get really complicated looking functions. And that's what bonding orbitals are. But anytime you can have a bonding orbital that looks like f plus g, you can also have an anti-bonding orbital. Which mathematically looks like f minus g. So if f plus g gives you constructive interference, f minus g gives you destructive interference. So instead of having these waves adding together, they cancel each other out. And so energetically, because if it's an anti-bonding orbital, we're actually limiting the amount of overlap you can have. We're actually saying that they're not allowed to overlap. Basically, we're trying to put these two orbitals together, but one of them has the opposite sign of the other. And so you get this opposite of a bonding orbital called an anti-bonding orbital. And so just mathematically, anytime you make a bonding orbital, there has to be a corresponding anti-bonding orbital that's higher in energy. We just don't usually put electrons into it because we fill electrons from the bottom up, right? From lowest energy, just like with electron configurations. We always start with the lowest energy orbitals, and then we add electrons till we run out of electrons, right? So the d orbitals still exist for hydrogen. We just don't have enough electrons that they matter. Anti-bonding orbitals work the same way. They're there, we just might not have any electrons in them. And with sigma bonds, this winds up, the gap between bonding and anti-bonding is a really large gap. It takes a lot of energy for most sigma bonds. And the stronger a sigma bond, the more downhill in energy the bonding orbital is, which means correspondingly, the more uphill the anti-bonding orbital, right? So the stronger a bond, the higher energy the anti-bonding orbital is going to be. So for sigma bonds that are really strong, anti-bonding orbitals don't typically matter that much. They're so high energy that we never see electrons actually getting put into those orbitals. If you got to high enough energy light, you could see that, which is why you wind up with high energy light can denature proteins and break chemicals down, because it has enough energy that you can move an electron from a bonding orbital to an anti-bonding orbital, which means chemical bonds start breaking apart. So, which is one of the reasons why you don't have chemicals, you don't have compounds in suns. In the sun, everything is high enough temperature, high enough energy, you can't form chemical bonds, because as soon as you form the chemical bond, you have you have enough energy that you just immediately put electrons into the anti-bonding orbital and they fly apart. Right, so that's part of what makes it a plasma, is that you have that high enough energy that you can't hold molecules together, which is kind of cool. On Earth, we frequently get to systems where the pi bond and anti-bonding orbitals are close enough in energy that they wind up being relevant. Most things that absorb light in the visible spectrum have a conjugated pi system. And most things that are organic, especially. Inorganic stuff gets a little bit different because we have d orbitals mixing in. But that's why most dyes, when you shine light on them, you're actually moving electrons from a bonding orbital to an anti-bonding orbital. In that the color of light, or the wavelength of light that it absorbs corresponds to the color that it's absorbing. Right, so in other words, what the colors that are being subtracted from the white light spectrum. Which is why pretty much all dyes bleach eventually, especially organic dyes. They eventually bleach out and become less intense colors, basically because the light eventually just breaks the molecules down. It's less common with things that are inorganic because we're dealing with sigma bonds in that case, which tend to be stronger even if they're still absorbing light in the visible region. All right, so how does this apply to conjugated dienes? Well, if we just think about 1,3-butadiene as having 3 unhybridized p orbitals we're going to mix together to make these pi bonds. So if we start with just we're just going to treat it like it's linear just for the sake of drawing this. It's really they're all trigonal planar. In order to get them to all line up so that you can have that orbital overlap, you need them to all have the same phase, and you need them to all be oriented in the right direction spatially. In other words, you need it to be flat. And so the lowest energy state that you can get is if all of your p orbitals have the same phase and they're all facing the same direction, you can get all of them to overlap at the same time. You get one cohesive bonding orbital. Well, but if we can combine all of them this way, there's also ways we could flip some of these. Every possible combination of these orbitals mixed together is going to have its own energy, right? So if they're all facing the same way, we could call that like flipping heads on a quarter 3 times in a row, 4 times in a row. But if you think about, if you change any one of those heads to something else, you're going to get a different orientation, right? A different configuration. And in this case, that means a different energy. Basically, the more you break up the orbital overlap, the higher energy that system will be. So if we add, and usually we talk about it in terms of adding nodes. A node is a place where you basically flip the phase from blue being on top to red being on top. Remember, phase is not quite the same as charge, but it's like a negative sign in the function. Right, so it's where a wave goes from up to down. So if you add a node, I'll go back to, you guys remember using guitar strings as an analogy, right? For doing this in Gen Chem, we first started talking about orbitals. This is like if you've got an open guitar string, it's vibrating. The lowest energy state is when everything's facing the same way. If you add a node, that's a higher energy wave, which means it's in our diagram, adding one node, it puts us higher in energy. If we added a second node, here's where it doesn't look exactly like a guitar string anymore. If you have two nodes, you can still have some overlap, but there's a lot less overlap because you had to flip signs twice. What's that?
Then it looks like a standing wave.
Right, and starts getting the functions start getting more complicated that allow us to do this. In theory, you could have a wave on a guitar string that looked kind of like this, but it's not going to be symmetrical. You'd have to be changing the wavelength in the middle. But if you did put a harmonic a quarter of the way up a guitar neck, your main, so let's see, half, quarter, quarter. Your main frequency is going to look like this. But there is some amount of frequency that looks like that. It's just not the primary frequency that you're going to actually observe. But you can try that. If you play any stringed instruments, try doing the is that the third harmonic? That'd be at the 5th fret on a guitar, I think. I think the 5th fret is a quarter of the way. So the 5th or the 7th. Well, now you're talking music theory and you've lost me. I don't know my music theory that well. But right, so if you do this, if you try that 4th harmonic that gives you the red waves, and then take your finger off it and let it vibrate, and then put your finger right dead at the 12th fret at half the wavelength, you should dampen a little bit of vibration. You're not going to kill the 4th harmonic that looks like the red wave, but you'll kill the blue harmonic. So it's, anyway, we're getting lost in the weeds here on the physics side. The point remains, though, that every time we add a node, we're going to increase in energy. And the more nodes and however many p orbitals we have overlapping is how many nodes we could get up to, or n-1. So if we have 4 p orbitals, we could have 3 nodes. The highest possible energy would be if we alternated phase every single p orbital. If we went heads, tails, it's going to be higher in energy than it heads all the way across. And so when we're trying to put electrons into these orbitals, when we're trying to see what the orbitals are actually going to look like, the orbitals that have electrons in them, we do it the same way we would with an electron configuration. You start at the bottom, the lowest in energy, and you add electrons till you run out of electrons. In this case, we're just talking about the pi bonds, so we only have 2 pairs of electrons for 1,3-butadiene, right? Because all the sigma bonds, their energies are all already set. they're lower in energy. We're talking just about the pi system, the p orbitals. So there's only 2 pairs of electrons. So the occupied orbitals are the ones, the 2 lowest energy orbitals out of that system. These orbitals still exist, but we call them unoccupied. Right? And so this interaction between, or where they cross over from occupied to unoccupied, is where all the interesting chemistry happens. Everything that's lower in energy than that is too stable to do anything with. It's a lot like when we're talking about the periodic table, we only care about valence electrons, right? Because those core electrons are too stable to do anything with. We really care in organic compounds about the frontier orbitals. And the frontier orbitals are the ones where you cross over between occupied and unoccupied. Right, and so this is what, when Kenichi Fukui, the Nobel Prize in Chemistry, was that idea of frontier orbitals controlling chemistry. And they're also known as the HOMO and the LUMO are the most important ones. HOMO stands for highest occupied molecular orbital, and LUMO stands for lowest unoccupied molecular orbital. So if we know that, this is one of the ways that we make tunable organic LEDs, where we can make organic LEDs that emit whatever wavelength of light we want or absorb whatever wavelength we want, is by basically tweaking the distance between the HOMO and the LUMO. Because this distance is going to control what wavelength of light it absorbs. Because to absorb light, it has to be able to move an electron from one energy level to another energy level. And so the easiest way to do that is going to be taking your highest occupied molecular orbital and bumping an electron into the LUMO. So by tweaking that gap between HOMO and LUMO, you change what wavelengths of light are absorbed or emitted. And when you look at an entire system, we're talking about just for one molecule. If we extend this same idea to dealing with a mole of molecules at the same time, or a solid material, you wind up with all these orbitals being slightly different in energy and sort of overlapping with each other, and you get what's called band theory, where you don't have one discrete orbital, you have a range of energies where you can find the HOMO and the LUMO. And so if you had a whole solid crystal out of 1,3-butadiene, you wouldn't have a HOMO and a LUMO. You would have the valence gap, or the valence band and the conduction band. And the distance between the two is called the band gap. So this is where semiconductors come from, basically, is this difference in energy between the HOMO and the LUMO. If there's a gap in between the HOMO and the LUMO, then you wind up with a semiconductor. And semiconductors are the basis for everything about modern society, just about. Computers, LEDs, photovoltaics, transistors are all semiconductors. And it all comes from frontier orbitals. We're just looking at them as though they were discrete molecules and not as a whole ensemble. Another place that chemists like music, I think, because you wind up using a lot of music terms in chemistry. Ensemble is actually a statistical thermodynamics term. A canonical ensemble means you have the entire population of molecules being represented. All right, so HOMO and LUMO, interesting. Why does it matter? And this is part, I'm going to go over it fast because we're going to need to go over it more than once anyway. So let's do it fast once and then we'll spend time with it. These conjugated dienes So this basically, we're adding a third type of reaction. So predominantly, we've been dealing with ionic reactions or free radical reactions, right? You can have reactions that are neither ionic nor radical, where they happen all simultaneously. And we've actually seen one of these already. When we used that peroxy acid to add an oxygen to, shoot, what functional group was that? Is that making a peroxide? Yeah, making a peroxide from an alkene is a pericyclic reaction, right? And it looked similar to these in that there's a whole bunch of red arrows showing all these electrons moving at the same time, right? You never had any one point that you actually had anything with a negative charge or a positive charge. You went from neutral to neutral just by drawing the right arrows from the right pi bonds. So these pericyclic reactions, they're called pericyclic because they almost always involve electrons, pi electrons, moving in a cycle, in a circular motion. And so the first one we'll look at is called a cycloaddition, where we can actually wind up, it's a similar net result to doing two additions at the same time. You wind up losing two pi bonds and making two sigma bonds. But there's never a point where you have a positive charge. There is no intermediate. It's one concerted reaction where you break two pi bonds at the same time as making two sigma bonds. Right? And so cycloaddition is the most common form. The most common form of cycloaddition is the one that's shown here. That's called the Diels-Alder reaction. And Diels-Alder has the net result of taking a conjugated diene and another pi bond, and you make a ring out of it. You can also have what's called an electrocyclic reaction, where you wind up rearranging pi bonds to make a new sigma bond and wind up forming a closed structure, linking the two ends basically. And so you have to have a conjugated triene for that to be very common, for that to be very stable. But you can see it with a diene. And then we can also have what's called a sigmatropic rearrangement, which is basically you don't have a net change in the number of pi bonds or sigma bonds, but you rearrange where they are. Right? And so the reason we spent that time talking about HOMO and LUMO is because it turns out which stereochemical product you get depends on what the HOMO and LUMO look like and whether or not you're doing the reaction with light shining on it. Right, so let's talk about the Diels-Alder reaction. And oops, I thought I fixed this one. It's what's known as a 4-2 cycloaddition. And 4 and 2 doesn't have to do with the number of atoms, it has to do with the electrons. You have 4 pi electrons on one side reacting with 2 pi electrons from the other side. And the net result is that we wind up adding these two molecules together. Right? And so it's always going to look pretty similar. For it to be for a Diels-Alder reaction to happen, you have to have a conjugated diene. And then you have to have another pair of pi electrons, the 2 here, and which is usually called a dienophile. Maybe you would never come up with that name yourself, but at the same time, we know phile means loving, right? So a dienophile is attracted to a diene. And the mechanism is always, for these cycloadditions, is always going to look pretty similar. It's all got to happen at once. And you're always going to make 2 new bonds, 2 new sigma bonds at the expense of 2 pi bonds. Right, and so it's been shown pretty conclusively, it's definitely a concerted reaction. There's no intermediate along the way. We can find a transition state energy that looks like all of those electrons being delocalized at the same time. Your new bonds are forming at the same time that your old bonds are breaking, and and leads straight from your reactants to your products. It is a reversible reaction. You can have what's called the retro Diels-Alder. Retro means backward, right? So a retro Diels-Alder just means if you go to a high enough temperature, you can get this reaction to happen backwards. Why would the high temperature favor the reactants here? Entropy. We make more pieces, right? It's basically an elimination reaction. If we go backwards, right? We're reforming pi bonds and breaking sigma bonds. So we get more separate pieces. That's transition state that I circled right in the middle though. That is exactly why we have to look at the orbitals. Because if we're having all of these electrons moving around at the same time, all your new bonds forming and old bonds breaking at the same time, that means that they have to be able to have their orbitals overlapping in a way. You need the right anti-bonding orbitals to be overlapping with the right bonding orbitals in order to make new bonds. And so and just a note here, that's sigma, right? And so we use call a sigma bond. If we draw sigma star, that's a sigma anti-bonding orbital. It's the shorthand for it. So you would also have pi and pi star. So if I say pi star, that just means anti-bonding orbitals. And here is where it gets complicated. If we do this reaction with different stereoisomers, we can see that we get stereospecific. It's a stereospecific reaction. We get stereospecificity. If we start with the molecule with our dienophile being cis, we get a cis product. If we start with our dienophile being trans, we get the trans product. And we can show what that might look like if we draw the transition state. Right, so if we draw, let's see how the best way, we start by drawing diene, and then we wind up with our dienophile coming in, and remember, these have to be coming in above or below. So this, I'm kind of drawing the red ones being a little bit smaller because I'm representing it coming from behind the board up to it. If we're going to have these bonds breaking and forming, we need our pi bonds to be pointed in the right direction, right? Really, we want the pi star orbitals facing the right direction so that you can start overlapping. And remember, the pi bonds for the blue diene are out of the board and into the board, right? If the atoms are flat in the board, the pi bond is out and in. So to take that pi bond and make a new sigma bond, we have to bring in this molecule either from behind the board and bring it up to the board, or start out here and bring it back. Right? You can't just slide it in this way, because then you can't have any orbital overlap between your pi bonds. And so then the transition state would look something like just like this, where you start having, okay, if this pair of electrons moves over there to make a new sigma bond, you got to make room. These electrons are going to come over to that carbon to make that new sigma bond. These electrons have to move over to make room, and they move over to make the pi bond that remains at the end. So because it all happens at the same time, and because spatially, we have to have the red molecule has to come from in front or behind. If it starts cis, it's going to end cis. Even I flipped it up, right? X is drawn sort of behind the blue molecule here. They still would both be facing the same way, right? It's so we do wind up, and that makes a lot of sense. You might wonder why I'm belaboring the point. And that's because, well, what happens when we start with a molecule that already has a ring as our diene? Now all of a sudden we're making a bicyclic structure. And all of a sudden, it's not just enough to know whether it's cis or trans, you need to know which version of cis and trans, because there's what's called endo and exo, where you wind up with them facing, you could have them both be exo or both be endo and pointed towards the larger ring, right? So we start getting these more complicated shapes. And we're going to keep coming back to, we need to look at the orbitals to know how this is all going to shake out. All right, we'll end there. It is hard to brominate. We are, speaking of labs and bromination, we're not doing a lab in lab today. We're going to assign your final project. It's week 10. So if I'm going to give you guys a couple weeks to write a lab report, you're going to propose a synthesis. Everybody's going to get their own synthesis. I'm going to give you a target, and then everybody's going to have access to the same stock room, which is not going to be the same stock room we have. It'll have some extra stuff and some gases and things like acetylene that we don't actually have on hand. And then I'm toying with the idea of having you actually perform one of the steps as part of your lab final, or we might save that for next quarter. Pick a couple of the steps in your synthesis and actually set them up and see if your procedure works the way you wrote it. So come to lab. We won't be doing lab. The assignment's probably available on Canvas right now, but I need to tweak it because it still has everybody's names in it from 2 years ago. I need to give all of you your own compound that you're going to synthesize, and everybody having their own compound means that everybody's allowed to work together, because you all have to solve your own and then write your procedure for it. It'll all be about 4 or 5 steps. All right. Stop recording.